Okay, so now let's talk about second order linear differential equations. Okay, so second order linear differential equations, ordinary differential equations, of course. Okay, so before talking about these, I want to talk about in a little bit more detail what do I mean by linear differential equation. Okay, given that what we have learned about first order linear differential equations. Okay, let's try to learn something from those. Okay, so suppose you have essentially this equation. Okay, so dy by dx is equal to say square root of 5. Now this is a non-linear differential equation. Okay, fine. I can recast, if you want, this equation in the form, okay, so that it looks analogous to a homogeneous linear differential equation, except that it's not linear. Okay, now of course solving this non-linear differential equation is straightforward, as you can just do a separation of variables so that you get this thing. Okay, and then you can integrate both sides so that you have 2 square root y is equal to x plus c, and that immediately leads you to that y is equal to x plus c over 2 whole square. Okay, let's check this. So from this you have dy by dx is equal to 2 x plus c over 2, right? And then you have another factor of half coming. Okay, so you have x plus c over 2, which is precisely equal to square root of y. Okay, given that y is equal to x plus c over 2 whole square. Okay, so yes, that's the solution to our non-linear differential equation. Okay, now let me call, for future convenience, this solution as y1. Okay, so I have that y1 is equal to x plus c over 2 whole square. Now the question that I ask, it's a very innocent looking question. Okay, given that y1 is a solution, okay, is k y1, where k is an arbitrary constant, also a solution? I'm using k for the constant because I already used c for the constant above. Okay, so that's my question. You'll see that for a linear equation, for a linear homogeneous equation, this will be true, that given a solution, then the multiple of that solution is also going to be a solution of your differential equation. But is it true for your non-linear differential equation? Well, it's easy enough to check that. If you have dy by dx is equal to square root of y, okay, then we know that since y1 is a solution, this has to be true. In fact, that's precisely what we checked above. Okay, then if I instead of y1 I substitute instead k y1, right, then using the rules of differentiation, since k is an arbitrary constant, that goes outside, so I have this thing, right? Okay, and this thing, of course, given that that y1 is a solution of my differential equation, okay, this differential equation over here dictates that this thing should be equal to k square root of y1. Okay, but if k y1 itself is a solution of my differential equation, then I must have that right. Okay, because my original differential equation, remember, is simply this. On the other hand, what I actually have is this thing, the d by dx of k y1 is equal to k times square root of y1. Okay, so evidently k y1 is not a solution of the nonlinear differential equation, whereas y1 is. Okay, and that's really the key point behind the simplicity of linear differential equations. Okay, on the other hand, so for linear differential equations, and this is true for higher order as well, if y1 is a solution, then k y1 is also a solution. Okay, let's check this claim. So to be more precise, what I'm talking about here is linear homogeneous linear differential equations. Okay, but most of the time we are interested in homogeneous linear differential equations because, as seen previously, finding out the solution of the homogeneous linear differential equation is the main part of the job. Once you have done that, solving finding the solution for the non-homogeneous differential equation is a simple extension of that. Okay, so let's check our claim. Okay, so for first order, we know our linear differential equation. Okay, so that's this. Okay, so if y1 is a solution, then I know that this has to be true. Okay, let's check if ky1 is a solution. So we say, okay, if ky1 is a solution, then the left hand side is equal to, okay, which in turn is equal to k right. Okay, fine, which is equal to k times okay, right. But since y1 is a solution of this differential equation, we know that this thing has to be equal to q of x, right. On the other hand, if k y1 has to be solution of your differential equation, then we must have that right, if k y1 is a solution of your differential equation. But that's not the case, once again. Okay, because you have over here you have this k. Okay, so you have that the derivative of k y1 plus p times k y1 is equal to k times q of x, not just q of x. Okay, however, if you had a homogeneous first order linear differential equation, then you would be fine. Okay, because then you have essentially that d by dx, that this thing plus p of x y1 is equal to 0. Okay, because now you're dealing with the homogeneous first order linear differential equation. If then you can go on and say, okay, what about k y1? Then you have, okay, that this thing is k1 plus p of x k y1, right? That's your left hand side, and this is equal to, of course, dy1 dx plus p of x y1, and this is equal to 0 because this thing is equal to 0 because y1 is a solution for your homogeneous first order linear differential equation. Okay, right. So the left hand side is 0. Okay, and since your original equation is this thing, okay, then that immediately implies that k y1 is also a solution. Okay, because essentially when you substitute k y1 for y, you get 0. Okay, so in other words, for a homogeneous first order linear equation, if y1 is a solution, then ky1 is also a solution. Okay. This is actually not at all a big discovery, because remember, for the first order linear homogeneous equation, we already have the solution. The solution to this equation was that this thing is equal to c e raised to power minus I, where I is the antiderivative of p. Okay, this is playing exactly the same role of k above. Okay, c remember is arbitrary. Okay, so c could be any value, and this function y would still be a solution of this differential equation. Okay, now I can recast what I'm doing in a fancier way. Essentially, I can talk about operators, differential operators. But before doing that, let me make one observation. Okay. Recall from your linear algebra that if you have a linear operator, or just think about a matrix A, okay, which acts on a column vector, okay, or a vector in general. You should talk about in abstract terms, x, okay, and this has to be equal to 0. Given a linear operator A, suppose you have found such a x. Okay, so you're given a linear operator A. Suppose you have found an x such that when A acts on x, you get 0. Okay, the 0 vector. Okay. Then it's trivial to show because A is a linear operator, then it is trivial to show that any multiple of x will also do the job. Because if you calculate this thing, since A is a linear operator, you can drag C outside and you're left with AX, right? But this thing is 0 because you're assuming that X has the property that when A acts on it, you get 0. So you get C times 0 and you get 0. Okay. So this property of homogeneous linear equation that we have discussed above is very analogous to this property of linear operators. Okay. And the correspondence carries on forward, okay, as we'll see. Okay, now going back to our first order linear equation, I can recast that in fancy language. Let me first of all define the differential operator. Capital D is just d by dx. Okay, so capital D is really only defined when you act on it on some function or y. Okay, so when d acts on y, that just means that we're taking the derivative of y. Okay, d square acting on y just means that you act on y twice with the derivative operator, so that means the double derivative of y. Okay, and so on. Okay, then I can also define the operator L as d plus p of x. Okay, oh sorry, there was a mistake above. Let me fix that. It should be y is equal to 0. That. Okay. Okay, if I define my operator L like that, then I know that L acting on y is simply equal to dy plus p of x times y. Okay, right? Okay, so I can then recast my first order linear equation as L x on y to give me q. Okay, so that's what I have. So I can recast my first order linear differential equation in terms of an operator, a linear operator. Now why am I calling it a linear operator? Okay, because if L acts on say c times y, where c of course is some arbitrary constant, then by definition I have that this is equal to d plus p of x on c y, and this is equal to d x on c y plus p x on c y. Okay, but d is the derivative operator. Okay, so c you can pull outside the derivative operator and you're left with dy, and p is just a function of x. So you can rearrange over there to get this thing, and this is equal to c times dy plus py, okay, which is equal to c times ly, okay. And that's exactly what you expect with linear operators. That's exactly what happens when matrices act on vectors, okay. So now let's discuss second order linear differential equations, okay. So second order linear differential equations, remember that you have a2 plus a1, where a2, a1 and a0 can be functions of x, any arbitrary functions of x, and this is equal to some function of x, okay. So this is your homogeneous second order linear equation. Similar to before, I can define an operator like this way, okay. If I act L on y, it's easy to see that I'll get oops. Just to be clear, d square means that you act on y twice with the derivative operator, okay. And this is precisely, so Ly is precisely the left hand side of your linear differential equation, okay. Fine. I can also very easily check, just as before, that this is true, okay. You can very well easily also check that okay, where y1 and y2 are any functions of x, that this will be equal to okay. So this is equal to and this of course is equal to exactly what you expect from a linear operator. So linear differential equations, the key point about linear differential equations, whether the first order, second order or higher order, although higher order is rare in physical applications, okay. The key point about linear differential equation is that you are dealing with linear operators, okay. Fine. So with that in mind, let's proceed now, okay. Okay, an equation that appears very often in physical applications, second order linear differential equation. The simplest case is when a2, a1 and a0 are constants, as in they are not functions of x, okay. So what I'll do first of all is I'll consider the simplest homogeneous second order linear differential equation that you can have, okay. Since it's homogeneous, the right hand side has to be equal to 0. So I can write a general homogeneous linear differential equation with constant coefficients as the following. You might be wondering what happened to A2. Well, I can divide, because I'm talking about homogeneous equations, I can divide the equation throughout by A2, okay, and then I can redefine A1 and A0. So I can always put my homogeneous linear differential equation into this form, okay. And to solve this equation, I can use my previous notation. So what I have over here is that I can write this equation as d square plus a1 d plus a0. So in other words, my linear operator is simply that, d square plus a1d plus a naught. Okay. What I can then do, okay, because a1 and a naught are constants, okay, I can factorize this linear operator. Okay, so you can factorize this operator. What do I mean by that? Essentially, it just means that you treat d that is appearing in this linear operator L as some algebraic quantity. Okay, so in other words, you have this equation. You just treat d as an algebraic symbol. Okay, so then you can factorize this quadratic expression into this form, where a and b are simply the factors of this, are simply the roots of this algebraic expression. Okay, so that's what a and b are. Fine, then I can write my original homogeneous linear differential equation in this form. Okay, remember, a and b are found by treating your L as an algebraic expression, and a and b are simply the roots of your quadratic expression. Okay, fine. Now this is true, so you want this equation to hold true. This is certainly going to be true if d minus b y is equal to 0. Okay. Notice what I've done. I've reduced my second order linear equation via factorization of my linear operator to effectively a first order linear differential equation. Okay, two first order linear differential equations. Okay, because this equation, this linear differential equation, can also be true if d minus a acting on y is equal to 0. Okay, and you can easily check that. In other words, since almost all of you have done quantum mechanics, what I can do is that you can work out the commutator of this operator d minus a with d minus b. Okay, and it turns out that the commutator is 0, which means that you can swap the order of d minus a and d minus b. That makes sense. Okay, because when I factorize it over here, I might as well have written this thing as d minus b d minus a. Okay, because a and b are just roots. Okay, it's up to me what I call a and what I call b. Okay, so in other words, I've reduced my second order differential equation to first order differential equations. Okay, and I'm happy with that. Okay, because I know how to solve linear first order differential equations. The solution to this is very easy. If you write it out explicitly, you have dy by dx is equal to by. Okay, and if you write this explicitly, you have dy by dx is equal to a y, right? And a and b, remember, are constants. Okay, because a and b are just roots of your L treated as an algebraic expression. A naught and a1, remember, are constants. Okay, the solution to this differential equation is straightforward. The solution to this is e raised to power bx. The solution to this is y is equal to e raised to power ax. Okay, fine. And then what about the general solution? Remember, if you're dealing with a second order linear differential equation, then you need to have two constants appearing. Okay, but I know something about linear differential equations now, homogeneous linear differential equations now. If this is a solution, then any multiple of this thing is also going to be a solution. Okay, so I can say that this thing is a solution of my linear differential equation. You can very easily check that by plugging this back in to your original differential equation. Assuming that e raised to power bx is a solution, you're very easily going to find that c1 times e raised to power bx is also a solution. Okay. However, since this is a solution as well, then this thing is also a solution. Okay. But what about the most general solution? Okay. It turns out that the most general solution is a sum of these two solutions. That just boils down to the fact that your L over here, this L, is a linear operator. Okay, so let's check that out. Suppose you have a second order linear differential equation and you have found one solution y1, you have found another solution y2. Okay, so then you say that okay, c1 y1 is a solution, c2 y2 is a solution, and my claim is that the sum of these is also a solution. Okay, so is this a solution? Let's check that out. Okay, checking it out is straightforward because I am dealing with a linear differential operator. So L acting on y is L c1 y1 plus c2 y2. Okay, and then using the property that this is a linear operator, you have c1 y1 plus L acting on c2 y2, and then again using that this is a linear operator, you have L y1 plus c2 L y2, but L y1 is equal to 0 because you are assuming that y1 is a solution of your homogeneous second order linear equation, and L y2 is also equal to 0 because again you are assuming that y2 is a solution of your second order linear differential equation, homogeneous. Okay, that's why you're getting 0. So this whole thing is 0. Okay, so in other words, if you have found two solutions, two independent solutions, okay, independent in this context means that the two solutions are essentially not the same. The two solutions are not multiples of each other. Okay, and I'll quantify that more rigorously later on. What do I mean by two independent solutions? But given that you have found two independent solutions, y1 and y2, the most general solution for your homogeneous second order linear equation is simply a superposition of those two solutions. Okay, that's the nice thing about linear differential equation. So in other words, the complementary solution, okay, in other words, the solution to your homogeneous linear differential equation is simply given by c1 y1 plus c2 y2, or in our case it's simply given by e raised to power bx. Okay, right, it's basically as if the solutions e raised to power ax and e raised to power bx form a basis for a vector space, and any vector within that vector space is a solution. Okay, and so you have this vector space of solutions to your second order linear differential equation. And let me do a quick example now. Suppose you have this differential equation, okay, d2y dx2 plus 5 dx plus y is equal to 0. So this is a homogeneous linear second order equation, and you can write this instead as d square plus 5d plus 4 acting on y is equal to 0. So the linear operator is d square plus 5d plus 4. You can factorize this operator as d plus 4, d plus 1. This is of course equal to 0. And then you can extract the solution from saying that okay, d plus 4 y is equal to 0, right? This implies that y will be, one solution is e raised to power minus 4x. On the other hand, you also have d plus 1 y is equal to 0, so you also have a solution y is equal to e raised to power minus x. The most general solution to your homogeneous second order linear differential equation is a superposition of these two solutions. C1 and C2 of course you find from the initial conditions or boundary conditions. Okay, so that's what you have. Okay, now I've been assuming of course that the solutions that you find are linearly independent. Now what do I mean by that? Remember that if you have two vectors v1 v2, we say that these two vectors are linearly independent if when you write down the following equation, the only solution to this equation is the trivial solution, that is c1 and c2 are 0. That's the only solution. There is no other solution. In other words, V2 is independent from V1. It does not contain V1. Okay. Think about this factorially. If V2 was parallel to V1, okay, then you have another solution where C1 is not equal to where C1 and C2 need not be equal to 0. Okay, so for example, if V2 is k some constant times V1, in other words V2 is parallel to V1, then you can write the above equation as C1 V1 plus k C2 V1 is equal to 0, right? Okay, and then you can say, okay, this equation can be satisfied if C1 plus k C2 is equal to 0, so that C2 is equal to minus C1 over k. Okay, so you can, one solution to this equation and this one would then be that C1 say is 1, and then C2 would be minus 1 over k. Okay, and so you have found one solution, actually infinitely many. You have found one solution at least where C1 and C2 are not 0. Okay, so extending this test for linear independence to when you talk about two functions is straightforward. Okay, so suppose you have two functions y1, y2. Okay, these are linearly independent if, exactly as for vectors, if given this equation. Okay, the only way that this equation can hold is if C1 and C2 are both 0. If this is the only way that this equation can be 0, then you say that y1 and y2 are linearly independent. Okay, so that essentially just means that y2 is not a multiple of y1, as you show for the case of vectors. Okay, let's see it another way. Okay, so suppose you are given this. Okay, right, so this is the equation that allows you to test whether or not y1 and y2 are independent or not. Okay, I can differentiate both sides of this equation with respect to x. Remember, y1 and y2 are functions of x. C1 and C2 are just constants. Okay, so I can write down C1 y1 prime plus C2 y2 prime is equal to 0. Right? Okay, fine. So now I have two equations. Okay, and I need to find out C1 and C2 from these two equations. Okay, that is essentially I need to find out whether they have to be 0 or can they be non-zero. Okay, so I can recast this equation in matrix form as follows. Of course, and if you remember from your linear algebra, if you could take the inverse of this matrix, okay, then of course you would immediately have that C1 and C2 have to be 0. So in other words, you want the inverse of this matrix to exist if C1 and C2 have to be 0. If the inverse of this matrix exists, then C1 and C2 are going to be 0, and correspondingly y1 and y2 are going to be independent. Okay, so the inverse of this matrix of course exists if the determinant of this matrix is not 0. Okay, so in other words, we define a quantity, the Wronskian, okay, as the determinant of this matrix. The determinant of this simple 2 by 2 matrix of course is simply, okay, that. So if W is not equal to 0, then y1 and y2 are independent, linearly independent. Okay, so that's my test. It's a very simple test to carry out. Okay, let's check that. So previously we have found that e raised to power minus x, we claim that e raised to power x and e raised to power minus 4x are independent. Let's check. Okay, so I'm saying that y1 is equal to e raised to power minus x and y2 is equal to e raised to power minus 4x. So first of all, I need to find y1 prime. Y1 prime of course is the derivative of y1. Okay, so that is minus e raised to power minus x, and y2 prime is equal to minus 4 e raised to power minus 4x. So w, the Wronskian, is y1 e raised to power minus x multiplied by y2 prime, which is minus 4 e raised to power minus 4x, right, minus y2, which is e raised to power minus 4x, and then you have y1 prime, which is minus e raised to power minus x, right? So that's what you have, minus y2 and y1 prime. Yeah, that's exactly what you have. So you have minus 4 e raised to power minus 5x plus e raised to power minus 5x, which is minus 3 e raised to power minus 5x, and this is not going to be, this is not equal to 0. Okay, you might be saying that okay, in general you might be finding that the Wronskian is 0 for some value of x. Okay, but you just need the Wronskian to be non-zero for some value of x, and that's it, they are linearly independent. Okay, so that's essentially how you find out whether you have two independent solutions to your second order linear differential equation or not. Okay, given two independent solutions, you can form a superposition of those two solutions to write on the solution for your homogeneous second order linear differential equation. Let me also note that we are writing our second order linear differential equation, homogeneous second order linear differential equation, in the form d minus a d minus b y is equal to 0, right? Now a and b are the roots essentially of the algebraic expression corresponding to your linear operator, and a and b can even be complex. In actual fact, if you look at the harmonic oscillator equation, okay, this one, a very basic simple harmonic motion equation. So for example, this comes about if you have a wall, you have a spring attached to it, and then you attach a block to it, and then you pull the block. Okay, the displacement of the block, if it's given from the equilibrium position, if it's given by x, then the force acting on the block will be minus kx, okay, due to the spring force, okay, by Hooke's law, and this will be equal to, by Newton's second law, that mass times acceleration. And so you can bring m to the other side, and you can define that your omega naught square omega naught square is equal to k over m. It's defined this way for future convenience. Okay, so k over m we define as omega naught square, and you then have that d2x by dt2 is equal to minus omega naught square x. Okay, that's where this equation comes from. Okay, and we want to solve this equation. So first of all, let's look at this equation. Given that we have done so much classification, introduced so much terminology, let's see what we can say about this equation. Okay, so this equation, if I bring omega naught square x to the left hand side, I can write as this. So first of all, of course, the independent variable now is t, and the dependent variable is x. Okay, so the first thing to notice is that this is a second order homogeneous linear differential equation. Okay, and you can solve this by writing this equation as d square plus omega naught square acting on x is equal to 0. Okay, of course the role played by y before is now being played by x, and the role being played by x before is now being played by t. Okay, so do we know how to solve this equation? You just factorize this linear operator. The factorization is straightforward over here. So you have d plus I omega naught d minus I omega naught x is equal to 0. Okay, so you see the roots now are complex, And that's exactly what you expect. Remember, the roots go up into the exponents, as we saw before. And what you expect from harmonic oscillator is, of course, oscillatory motion. There is no track force, there is no damping over here. Okay, so you expect some oscillatory motion. You're not going to get oscillatory motion if the exponent of your exponential function is a real number. Okay, but if it's complex, then yes, that does correspond to and fro motion. Okay, so we already know how to solve this equation. Then you, because we know that if you have d minus a, d minus b on y is equal to 0, let me recall that then the solution is c1 e raised to power ax plus c2 e raised to power bx. Okay, assuming that a is not equal to b, because if a is equal to b, then of course you're just dealing with the repeated root situation, and then the two solutions are not linearly independent. But if a is not equal to b, you can very easily calculate the Wronskian, and that turns out to be non-zero, so you have two independent solutions. Okay, it turns out, of course, in this case, for the simple harmonic oscillator case, a is not equal to b because a is I omega naught and b is minus I omega naught. So we can straight away from this write down x as a function of t. You get c1 e raised to power minus I omega naught t plus c2 e raised to power plus I omega naught t. Okay, so due to the Euler identity, you can straight away identify that these two correspond to oscillatory motion with frequency omega naught. That's why we called the combination k over m as omega naught square, because later on square root of k over m does correspond to the frequency of motion. Okay, angular frequency. Okay, now one disturbing thing that might occur to you is that, okay, this is the position of your block, something undergoing simple harmonic motion. Okay, but this thing, of course, is complex. Okay, so this has to be real, while these things are complex. Okay, so how do we reconcile that? Okay, remember, you also have these constants. Okay, so first of all, let me use the Euler identity to expand this. So you have cosine of omega naught t minus I sine of omega naught t, right, plus c2 cosine of omega naught t plus I sine of omega naught t. Let me just group terms now. So I have c1 plus c2 cosine of omega naught t plus you have ic2 minus ic1, okay, sine of omega naught t. Okay, fine. Now I also need that I can also impose the fact that x of t has to be real. Okay, so if x of t is given by c1 e raised to power minus I omega naught t plus c2 e raised to power I omega naught t, if this is equal to x star t, then I must have that this thing. Okay, fine. And then if this has to be equal to this, okay, then I must have that c1 must be equal to c2 star. Okay, right. You can also say that, okay, c2 is equal to c1 star, but that's just a complex conjugate of this equation. Okay, so there's really only one condition. Okay, so c1 is equal to c2 star, otherwise your position is not guaranteed to be real. Okay, fine. If that is the case, then going back to this thing over here, I can immediately say that, okay, since c2 star is equal to c1, I also have that c2 is equal to c1 star. Okay, I can plug this thing over here. Okay, So because C2 is equal to C1 star, and then I'll get as coefficient of cosine omega naught t C1 plus C1 star. Okay, but that is guaranteed to be real. Okay, so I can then define C1 plus C1 star, which is guaranteed to be a real number, as some new constant capital A. Okay, similarly I also have this thing, right? Let me just change this thing, right? Okay, and C2 minus, so I have essentially I C2 minus I C1 over here. So I have I C2 minus C1, and this is equal to I C2 minus C2 star, because remember C1 is equal to C2 star. That's the condition you derive from here. And C2 minus C2 star, whatever C2 is a complex number, you subtract from it its complex conjugate, that is going to give you a purely imaginary number. And a purely imaginary number multiplied by this I is going to give you a purely real number. Okay, so I can define IC2 minus IC1, this thing over here, as just some real number, which I say as capital B. Okay, so in other words, I can write finally my x of t as some real constant multiplied by cosine of omega naught t plus another real constant sine of omega naught t. Okay. The actual values of a and b, of course, are determined from the initial conditions, or in other words, in this context, exactly when you start your clock. Okay. Okay, so before moving on, let me discuss the case where you have a repeated root. Okay, so suppose as a concrete example, so suppose you are dealing with this differential equation. Okay, minus 6 x plus 9y is equal to 0. Okay, so you have this differential equation. You can recast this, of course, as d square minus 6d plus 9 acting on y is equal to 0. Okay, and then you can factorize your operator to get d minus 3 y is equal to 0. So you see, now you have a problem, because that's exactly what I meant by a repeated root. You can figure out that one solution is e raised to power 3x. Okay, but how do you figure out the other solution? And that solution has to be linearly independent from this first solution, e raised to power 3x. So you cannot write e raised to power 3x again. Okay, so how do you figure that out? Well, one way would be that, okay, you can define a new variable. Okay, you can define this as d minus 3 times y. Okay, now let me just do it in full generality. Suppose you have a repeated root. Okay, so you have your differential operator becomes d minus a y is equal to 0. This is just the previous case, except that now a is equal to b. Okay, so now I define u as d minus a times y. Okay, so then this differential equation I can write as d minus a times u is equal to 0. Okay, and I can solve this differential equation for u. I immediately get that u will be equal to e raised to power ax multiplied by some constant. Okay, that is my solution to this differential equation. Once I have the solution to this differential equation, I can go back to this differential equation. I can say that d minus a y is equal to u, which in turn is equal to a e raised to power ax. Okay, so in other words, dy by dx minus ay is equal to a e raised to power ax. So see, once again I've reduced my second order problem to a first order problem. Okay, so this is a linear first order differential equation. Okay, remember, we know how to solve equations of this form: dy by dx plus p, where p can be a function of x, is equal to q, where q can be a function of x. The solution to this differential equation, if you recall, is given by c e raised to power minus I, where c is a constant, plus e raised to power minus I q e raised to power I dx. That's your solution. For our case, let me just quickly work it out over here. For our case, we have that in this equation, we have that p is just a constant, p is equal to minus a, okay, right? So I is just going to be minus ax prime, okay, because I is the antiderivative of p. And what else do we have? We have q is equal to a e raised to power ax, okay. So I figured out this time, because this thing is going to just be c times e raised to power minus ax, okay, plus I also have e raised to power minus ax over here, but then I have this antiderivative that I need to work out. So q e raised to power I dx is equal to, and q is going to be a e raised to power ax, and then e raised to power I is e raised to power minus ax dx. So this thing is just going to be equal to ax, okay. So what do I get then? I just plug this thing back here, so I'm going to get y is equal to c e raised to power minus ax, right? Wait, hang on. Yes, this is going to be c e raised to power plus ax, because I is minus ax and there's another minus sign over here, and you also have plus e raised to power ax, and then this thing is going to be a times x, right? Okay, so I can write this thing as a x plus c e raised to power ax, okay. That's my solution. Okay, in other words, the solution when you have a repeated root is a superposition of e raised to power ax and x e raised to power ax, okay. So your linearly independent functions now are not just are going to be e raised to power ax, are not just two exponentials. Those two exponentials won't give you two linearly independent functions, rather your linearly independent functions are going to be e raised to power ax, where a is your repeated root, and x multiplied by e raised to power ax. There's another way to see this. So when we had two distinct roots, my general solution was of the form right. So that was my general solution. Now suppose that your roots are not distinct; they are the same, okay. But suppose that the parameters in the differential equation are such that they gradually approach each other, okay. So they are actually not the same, okay, but I'm making them the same. I'm making them approach each other, okay. So in other words, I'm saying that b is equal to a plus a very small number delta, okay, and at the end of the day I'll make delta go to 0, okay, so that the two roots are actually the same. Let's see what happens then. So then I'll write y is equal to c1 e raised to power ax plus c2 e raised to power ax e raised to power delta times x. Delta, this is delta multiplied by x, okay, not change in x, okay. So this thing I can write then as e raised to power ax plus c2 e raised to power ax, and since delta is I'm assuming to be very small, I can do it. This is expansion for the exponential, so I get this 2 first order, okay. And then I can write c1 e raised to power ax plus c2 e raised to power ax plus c2 times delta, right? And what do we have? c2 times delta times x times e raised to power ax, okay. So I can write this as c1 plus c2 e raised to power ax plus c2 delta times x e raised to power x. I can then redefine my c1 is plus c2 as a new constant capital A. This is a new constant capital B, so that my general solution is some constant determined by the initial conditions multiplied by e raised to power ax plus some other constant again determined by the initial conditions multiplied by x e raised to power ax. Exactly the same as before. Okay. With this in hand, let's analyze damped harmonic oscillator motion. Okay, so we've already analyzed this equation, right? So this equation, if you recall, came about because we analyzed that okay, there's a block attached to a spring, and then the block is, you pull the block and then let it go, and that's essentially the equation of motion for the moving block, and we got that the block oscillates. Okay, fine. Right, so let's just recap what we found there. So we found that x of t we found is a cosine of omega naught t plus b sine omega naught t, right? Where a and b are determined by the initial conditions. Alternatively, I can also write this as c cosine omega naught t plus phi, or also as d times sine omega naught t plus phi. And you can figure out the relationships between a and b and c and d. Okay. Right. So if we have damped harmonic oscillator motion, okay, which means that friction is acting. Okay. So I have to put that the friction force into Newton's second law as well. Okay. So there are actually two types of friction. There's dry friction. Okay. And then there's wet friction. Dry friction is the type of friction that you are most familiar with when two surfaces rub against each other. So the dry friction, the kinetic friction is mu times n. Okay. Wet friction occurs when you really lubricate a surface. Okay, so the block is sliding on a very well lubricated surface. In that case, the friction force is actually proportional to the velocity of the block. Okay. It's much more difficult to deal with the case of dry friction. The solution of differential equation are much more complicated, okay, compared to wet friction. So what I'll do over here is that I'll assume that there's wet friction that's present. Okay, so let me then write down the equation of motion. So Newton's second law says that mass times acceleration of the block is equal to the net force on the block, which is minus kx. Okay, and you have minus L dx by dt. Okay. L is essentially the proportionality constant that goes over here, okay, to give you the friction force. Okay. Right, so then you just have to solve this equation. So you have m d2x by dt2 plus L dx by dt plus kx is equal to 0. So this is a linear second order homogeneous equation. Okay, so once again it's a homogeneous equation that is directly appearing in your physical application. Okay, usually non-homogeneous equations appear when you have some driving term. Okay, so if somebody was actually pushing the block periodically, then you would have to deal with a non-homogeneous equation. Okay. But anyway, so here we are. Okay, so we put this into standard form. So I write this as plus L over m dx by dt plus k over m x is equal to 0. For later convenience, I define a new parameter b, which you might be thinking I'll be defining it as L over m. Okay, but I actually define 2b as L over m. This factor of 2 is just for later convenience. Okay, so that I don't get extra pesky constants later on. Okay, this k over m, of course, I define as omega naught square, same as before. Okay, so then the differential equation that I need to solve is then d2x by dt2, right? Okay, plus 2b dx by dt plus omega naught square x is equal to 0. Okay, so that's the second order homogeneous linear differential equation that we need to solve. To solve this, since 2b and omega naught square are constants, we know how to solve this. I can just rewrite this differential equation as this thing. Okay, and then I can factor this linear operator. I can just find out the roots. Okay, the roots will be given by, you just apply the quadratic formula. So the roots are given by minus 2b plus minus 4b square minus 4 square divided by 2. Okay, and this of course is minus b plus minus square root of b square minus omega naught square. So that's essentially very good. Okay, so the one of the roots I called as lambda. I'm not using a and b because I'm already using b for the damping coefficient. Okay, related to the damping coefficient. So lambda is minus b plus square root of b square minus omega naught square, and mu is minus b minus square root of b square minus omega naught square. Okay, fine. And but now the character of my solution depends on what's happening over here. Okay, so I have three cases. If b square is bigger than omega naught square, then of course I get some solution. Okay, so let's analyze a solution where you have b square bigger than omega naught square. What happens then? Then my x of t is going to be given by constant e raised to power lambda t plus c2 e raised to power mu t. That's fine. And c1 e raised to power this is going to be e raised to power minus bt e raised to power square root of b square minus omega naught square t, and you will have essentially plus c2 e raised to power minus bt e raised to power minus square root of b square minus omega naught square t. Okay, right. Notice that whatever number pops up from here, that will be smaller than b. Okay, so the whole thing over here, the exponent is going to be some negative number multiplied by negative real number multiplied by t. Okay, and that's also the case over here. So you have an exponentially decaying solution. Okay, this is the overdamped case. Okay, you don't have any oscillatory motion over here. The damping is so strong. Remember, we quantifies the damping. The damping is so strong that essentially your mass returns quickly to the, well, it depends on the damping coefficient, but the mass does not execute any oscillatory motion, rather it just returns to equilibrium. Okay, the opposite case, where omega naught square is bigger than b square, that obviously means that the damping is weak. Again, you have x of t given as c1 e raised to power lambda t plus c2 e raised to power mu t. Okay, but now if you notice in lambda, since omega naught square is bigger than b square, this thing in the square root is going to be negative. Okay, so to deal with that, I first rewrite my lambda as minus b plus I omega, and mu as minus b minus I omega, where I have defined omega as square root of omega naught square b square, and omega is now real. Okay, because omega naught square is bigger than b square. So I can then write my solution as c1 e raised to power minus bt e raised to power I omega t plus c2 e raised to power minus bt e raised to power minus I omega t. So this thing I can write as e raised to power minus bt multiplied by c1 e raised to power I omega t plus c2 e raised to power minus I omega t. Okay, this thing in the square brackets is exactly the same as before, as we got for undamped motion, where there was no damping present. This is just simple oscillatory to and fro motion. The only difference now, of course, is that the frequency is different, and there's also this exponentially decaying envelope. So essentially, the graph would not be something like this, but rather it would be exponentially decaying as well. Okay, so you have something like this, which is exactly what you expect from underdamped motion. Okay, the third case, so this is underdamped motion. Okay, so you have to and fro motion, except that there's a little bit of damping, so energy is continuously being taken out of the system. Okay, and the amplitude of your oscillations progressively decreases. The third case is critical damping. in this case you just have that b square is equal to lambda. In this case you have a repeated root because lambda is equal to mu is equal to minus b then, because b square is equal to omega naught square, and this thing in the square root becomes 0. Okay, but we know how to deal with this equation. The solution is simply given by c1 e raised to power minus bt plus c2 times t e raised to power minus bt. Okay, and so once again we don't have any oscillatory motion. Okay, so the mass executing simple harmonic executing the mass experiencing this damping force, okay, as well as the spring force, does not execute any oscillatory motion, rather it returns to equilibrium, okay, without undergoing any motion. Okay, right. So but keep in mind that the differential equation that you saw over here, this differential equation, you see a very similar differential equation in many other contexts as well. So for example, if you are analyzing an RLC circuit, you see exactly the same differential equation. So the importance of this simple differential equation is not just restricted to analyzing blocks attached to springs. It occurs in many different scenarios. Okay, so you have to be good at recognizing, okay, the forms of solution that you can have with such a differential equation.